8.3 making molecules, mole to mole conversions. In a balanced chemical equation, we have a recipe of how reactants combine to form products. The following equation shows how hydrogen and nitrogen combine to form ammonia. For example, we can take 3 hydrogen molecules and break the bonds between them, this nitrogen molecule, and remake nitrogen-hydrogen bonds to make 2 molecules of ammonia from 3 molecules of hydrogen and 1 molecule of nitrogen. So, in other words, 3 molecules of hydrogen in the gas phase plus 2 nitrogen, 1 molecule of nitrogen in the gas phase goes to yield 2 molecules of ammonia in the gas phase. The balance equation shows that 3 H2 molecules react with 1 N2 molecule to form 2 NH3 molecules. We can express these relationships as ratios. So we can express them as molecule ratios, or we can express them as mole ratios. 3 moles of H2 for every 1 mole of N2 for every 2 moles of NH3. If we have 3 moles of N2 and more than enough H2, how much NH3 can we expect to make? This is a question we can answer using this balanced equation. We can strategize by drawing a solution map that begins with moles of N2 and ends with moles of NH3. The conversion factor comes from the balanced chemical equation. We're going to use the balanced chemical equation to get from moles of N2 to moles of NH3. And what we will focus on is that for every 1 mole of N2, there are 2 moles of NH3. The relationship used, 1 mole of N2 is 2 moles of NH3. So we write our given 3 moles. If we have 3 moles of N2, for every 1 mole of N2, we have 2 moles of NH3, gives us 6 moles of NH3. We have enough N2 to make 6 moles of NH3, assuming that we have an excess amount of hydrogen. When water is formed from hydrogen gas and oxygen, we can write a chemical equation. The chemical equation would be hydrogen gas plus oxygen gas goes to form water, liquid. Okay, we need to balance this equation, so we need a 2 here, which makes us have a 2 there. How many moles of H2O, so question mark goes over our H2O, and we're looking for moles, result from the reaction of 24.6 moles of O2. So 24.6 moles of O2. Well, we start with our given 24.6 moles of O2. Okay, let's change our pen. And we multiply by for every 1 mole of O2, we get 2 moles of H2O. Okay, so now we take our calculator and we say 24.6 times 2 gives us 49.2 moles of H2O. Okay, so that's how we do that problem. What if we have a problem that says how many moles of sodium oxide can be synthesized from 4.8 4.8 moles of sodium, so we're just going to have sodium, solid, reacting with how many moles of sodium oxide can be synthesized from 4.8 moles of sodium, assuming that more than enough oxygen is present. So we're going to have oxygen gas. This is going to be a synthesis reaction that makes sodium oxide, NaO, solid. Okay, so if we have 4.8 moles of sodium, then we are looking for how many moles of sodium oxide can be produced if we have excess oxygen. So we start from our given, which is 4.8 moles sodium. Okay, we got to go back up here because we forgot to do something. We forgot to balance our equation. We need a 2 here, which makes us have a 2 here. We can get out of moles of sodium and into moles of sodium oxide because we know that for every 2 moles of sodium, 2 moles of sodium oxide are produced. So for every 2 moles of sodium, 2 moles of sodium oxide are produced. So if we say we simply have an answer here, since we say 4.8 times 2 divided by 2, we get the answer is 4.8 moles. So we're going to produce the same amount as we put in of sodium, but it's moles NaO. Okay, a chemical equation contains conversion factors between moles of reactants and moles of products. We are often interested in relationships between mass of reactants and mass of products. The general outline for this type of reaction is to go through moles. So we'll have to get from moles of A to moles of B, and we'll use the molar mass or the atomic mass to do that. So we can go from mass of A to moles of A to moles of B to mass of B, and I'll show you an example. Let's look at this problem. Okay, how many moles of CO2? So if we come up here, we're going to write question mark, moles of CO2. How many moles of CO2 are produced from the reaction of 355 grams of octane? So we got 355 grams. Okay, well, these are not gram ratios here. They're mole ratios, so we need to get out of grams into moles. So we say 355 grams C8H18. Now we've got to use the formula mass to get out of grams and into moles. In 1 mole, and I'll do the math to get what the molar mass is. So I've got 12 times 8 plus 18 gives me 114 grams in 1 mole. Then we have, and that is C8H18. Okay, now for every 2 moles C8H18, how many moles of carbon dioxide are produced? 16 moles of carbon dioxide are produced. Okay, so now if I do the math, then I say 114, I say 355 times 16 divided by 114 divided by 2. And I should do that one more time. 355 divided by 114 times 16 divided by 2 equals 24.9. So it's 24.9 moles CO2. How many grams of CO2 are produced from the reaction of 45 grams of oxygen, assuming excess octane? So now we want to look at the number of grams of oxygen. How many grams of CO2 are produced from the reaction of 4.5 grams of oxygen assuming excess octane. Okay, so we start with our given. We start with our 4.5 grams of oxygen. Okay, so now we have 4.5 grams of oxygen. For every 1 mole of oxygen, there are 32 grams of oxygen, because there's 2 of them, it's a diatomic. For every 1 mole, for every 25 moles of oxygen, there are 16 moles of carbon dioxide produced. Okay, but we want to know how many grams of CO2. So for every 1 mole of CO2, there's 44.0 grams of CO2. Take my calculator, do the math. 4.5 divided by 32 times 16 divided by 25 times 44 equals 3.96, or if we want to do the right number of significant figures, which would be 2 in this case, will be 4.0 grams CO2. Okay, so in the back of the book, it is very, very important that you do these example problems. Look at example 8.1 on page 252, example 8.2 on page 255, and example 8.3. End of chapter problems 8.8 and 8.9. These are examples that are worked out. And then do the end of chapter problems and check the blue in the back of the book.